This is a lesson on parabolas, a particular type of function. Now parabolas are particular in that to get the y coordinate you always have to square the x coordinate. This takes us to the parent function, which is very simply the basic function obtained by squaring x. So your y coordinate is always obtained by squaring an x value. Even better is to write f of x is equal to x squared, because f of x just stands for y coordinate. Quite interested in what this parabola looks like. So remember, if you don't know what a function looks like when you graph it, you take a whole bunch of points which randomly and you plot them. So if we take a random x value, let's say an x value of 1 because it's nice to work with, the y coordinate will be 1 squared, which is 1, and so the point you plot is 1 and 1. Right, 1 on the x-axis and 1 on the y-axis. This is just a rough sketch, but the point we're plotting is 1 for x, 1 for y, so it's about there. I want another point to get more of a picture, so what if we had an x coordinate of 2, then the y coordinate will be 2 squared, obviously that's 4, and so the point we plot is 2, 4. Okay, again remember this is a bit of a rough sketch. I can keep going. I'm also interested in what's happening on the left hand side of the y-axis. If I want to go on the left hand side I need negative x coordinates, so let's pick an x coordinate of -1. So y equals -1 squared. Remember you're squaring the whole, -1 the negative as well. Negative times negative is positive, and so you get -1, 1 as the point. Let's plot. Notice the symmetry there. We plot one more point, let's say an x coordinate of -2. The y coordinate will be -2 squared, which is 4, which gives us another point. Notice whenever you square something, negative or positive, you get the same answer. So this thing is turning out to be quite symmetrical. So now we can join the dots as carefully as possible to see what it looks like. Note that we're allowed to join the dots because our domain is all real numbers. There's nothing which x can't be. So if you were asked for the domain of the parent function parabola, you would give all real numbers and you'd write that symbol like that. Similarly, if you were asked for the range, remembering that range is all the possible y values, then you'd have to look carefully. Can y be anything? Well, actually no, it can't. Y can't be a negative value. If I take -3, for example, there is no y coordinate of -3 on this parabolic function. So that gives me a bit of a hint. Y can't be negative. Y is actually only positive value, so y is greater than 0. Can it be 0? Oh, well, you know what? It can be, because if x is 0, y can be 0 squared, which is 0, and so the origin is a point which I plotted already without thinking about it. So we could be equal to 0, and we have to indicate that when we write the range inequality. Notice you can also write this in interval notation. It could be 0 or bigger, so the smaller one goes on the left, the bigger thing goes on the right. It doesn't stop, it can keep going on forever, and so we show that with the infinity sign and an open bracket. Notice the arrows on the end indicate that the domain and range keep going on forever. This leads us to the general parabolic function. The general parabola has the equation y equals, or f of x equals ax squared plus q. So let's not freak out about that. Let's have a look at what this means. Well, in this diagram, I've plotted y equals ax squared plus q and y equals x squared. Now to start off with, my a and my q values are q value of 0, so I'm not adding anything, and my a value is 1, so I'm not multiplying by anything, so that's why the two graphs are lying on top of each other. But if I start to play around with, let's say, the q value, notice what happens. It's translating the graph up. So if I have a q value of 2, it's translated the graph up by 2 units. Every point is 2 units higher than where it was. So that point there is now 2 units higher. That point there is 2 units higher. And similarly, if I use different q value, it's going to go, let's say if q is 2.5, then it's going to be 2.5 units higher than what it was on the parent. I can do the same sort of thing, but what if I make q negative? Well, no surprises there. It's translating my graph down. So if q is half, it's translated it half a unit down. Every point is half a unit lower than what it was before. Notice that happens to every single point on the parabola. Now, what happens if we play around with the a value? Well, if I make the a value bigger, look what's happening. What is it actually doing? Well, interestingly, it's stretching the graph. It looks like it's making it thinner. But if you watch carefully, that point that started there at 1, 1 has moved up to 2. It's doubled its y value. Notice up here, let's say, this point which started at 2 for the y coordinate, 2 for the y coordinate, double 2, you get 4, and look what's happened, it's doubled up to 4 there. So every point has gone up in a different amount, but it's a factor, it's doubling it. The point at the origin is 0. 0 times 2 is still 0, and so it's still at the origin. If I take a different a value, same sort of thing happens, but by a different factor. So every point is times by 2.5. Every y coordinate is times by 2.5. What happens now if I make the a coordinate a fraction? Well, it seems to flatten the graph out, but notice it's really doing the same thing. Here a point which is up at 4, half of 4 is 2, and look, the new point's down at 2. Half of, let's say, 3 is 1.5. Look, there's a point at 1.5. Half of 1 is a half. Well, there you go. What happens if I make the a negative? Well, as you can see here, it's reflecting the graph in the x-axis. So what was up here at, let's say, 2 is now down here at minus 2. The point was at 1 is now down at minus 1. And reflecting 0 in the origin is still at the origin. So let's formalize that. If we look at the general equation, y equals, or f of x equals ax squared plus q, we've seen a couple of things. With the q, we've seen that that affects a translation up or down. Notice it only went up or down, it didn't go left or right. We knew it was up if we took positive q values, and we knew it was down if we took negative q values. Okay. Notice something that I didn't point out on the picture is that if I have a q value I've translated up, because the parent function was having a y-intercept at the origin, if I go q units up, then my new y-intercept is going to be q units up from the old y-intercept at the origin. So there's my y-intercept. Notice also we talked about the a value, which stretches, and that's a pretty slang term. The proper word is dilates the function vertically, so by a factor of a. And notice also if a was negative, then we know that we had to reflect in the x-axis. Easy done. Don't forget as well, people seem to get freaked out about it, f of x is just your y coordinate. So this is saying y is ax squared plus q. Depending on what q and a's are, is going to determine what our graph looks like. So let's try and draw one. If they ask us to draw y equals, or f of x equals 4x squared minus 9, we need to get some information about it. Now I recommend that you first think about it before you draw it. We know that the a value is positive, so it's not reflected. It's going to be a normal smiley parabola, but it's got a q value of minus 9, which means a translation up or down? Down 9 units. And so that's kind of what we're expecting. We're expecting a y-intercept at minus 9, and that's what we're expecting. We should go and do some calculations to check our expectations. So if we had to work out the y-intercept, well, on the y-intercept, on the y-axis there, we haven't gone left or right, so we know our x-coordinate is going to be 0, and we use that to solve for the y-coordinate of the x-intercept by substituting that in. So you can see here we get 0 times 4, which is 0, minus 9, which is minus 9. Hey, that's what we were expecting. And so we can plot that. We keep going. We should work out our x-intercepts. Notice here we're expecting 2 x-intercepts. So let's see how that works out. Well, if we want an x-intercept, we're wanting points which cut the x-axis. That's going to be points which haven't gone up or down. They're only on the x-axis, and so our y-coordinate in this case is 0. It's always kind of opposite to what you expect. And so if y is 0, that means that, well, we know y is 4x squared minus 9. That's what's going to be 0. We know how to do quadratic equations, so we just do that quickly. It's difference of 2 squares. Factorize it, and we know that one or the other of those factors has to be 0. Because think about it, if neither of them were 0, well, you can't multiply two non-zero things and get 0 for an answer. That's never going to happen. So we get one x value answer of 3 over 2, and we get another x value answer of minus 3 over 2, which gives us 2 points to plot. 3 over 2 and 0, and minus 3 over 2 and 0. So we go and plot them. 3 over 2 is about here. Notice I'm really not drawing this to scale, and that's fine. You're not expected to, but just be consistent. So if I'm putting that, that far away from the origin on the right, the negative 3 over 2 should be the same distance from the origin on the left. Notice the symmetry that's happening. Every point, every parabola that we've drawn so far has the y-axis as an axis of symmetry. Everything is symmetrical about that line. And so when you've got one x-intercept, you can predict another. So we're now allowed to join the dots on that graph and see what it looks like. Try and draw it a little bit less skew than me, but there you go. Remember to put the arrows in the end to indicate that it keeps going on forever, and there you go. We can sketch another parabola, and let's do that. We're going to sketch y equals minus x squared minus 1. So again, let's see what we expect to happen before we sketch it. We're expecting that this is going to be reflected in the axis, the x-axis, because of the negative a value. So we're expecting sad-faced parabola, and we're expecting a translation of 1 unit down because of that minus 1, and so we're expecting something like that, very roughly. Can predict fairly easily that the y-intercept is going to be minus 1 for y, but we can check that. The x value is 0, the y coordinate is going to be minus 0 squared minus 1, which is minus 1. So our y-intercept is exactly what we expected, 0 and minus 1. Now, if we want x-intercepts, well, if we just blindly work out x-intercepts, we're going to put y equals 0 because we haven't gone up or down, and we're going to solve for x. Remember, the y is also minus x squared minus 1, so we're letting that be 0 and we're solving. But if you solve that, well, normally you're going to solve quadratic equations by having all the x squareds on the same side. But in this case, it's probably going to be better to say, well, let's add x squared to both sides. That tells us that x squared must be minus 1, which isn't possible. Okay, so that means that there's no solution. Does that make sense? Well, hold on a minute, we might have even wasted our time. If you look at our original prediction, we knew that it was sad-faced, we knew that it had translated 1 unit down, so we knew there were no x-intercepts. No surprises. But once you have that situation, you do need another point to plot. So you pick any other random x-coordinate, very randomly, so perhaps you pick an x-coordinate of 1, which is going to tell you that y is going to be minus 1 squared minus 1, which is minus 2, so we have a point to plot. By symmetry, we technically have another point, minus 1, nope, that's 1 and minus 2, and so we can join our dots as we did before. But make sure you indicate that other point. We're going to continue on another video working backwards from the way we've done and doing a nice mixed question. Please be sure to watch the next video.